Hello, everybody. I hope all of you are doing well and staying safe. So, we're going to look at a problem on the method of sections. Okay, and my idea is instead of spending another lecture defining what the method of sections is and so on, I think the best way to learn this is by solving a problem. Okay, and as I'm solving this problem, I'll outline some of the important ideas that we make use of in a method of sections. Okay, so let's say that this is a problem. Okay, using the method of sections only. Okay, obtain the forces in the bars ED, EH, and GH. Okay, so that's the first thing that you got to do. And then by inspection, you want to find out if there are any zero force members. Okay, and by inspection only, find out if there are zero force members. Any zero force members are present. Okay, so the typical thing I do is I start off by looking at what the zero force members are, and there are some forces acting on this body. These forces have a magnitude of 40 kilonewtons. Then here is one with a magnitude of 50 kilonewtons, and then these two here are 30 kilonewtons and 40 kilonewtons each. Okay, so these are all the forces that are acting at some of these things. There is a roller that you're seeing here. So this is a roller, and then this is a pin support. Okay, so this is what we have going on for us, and my first step is to actually find out, okay, what are the zero force members. So I'm going to copy this figure. Okay, I think I missed out copying pin A, but I'll write it down again. So let me look at what the zero force members are. Okay, so typically if I were teaching this class in person, right, this is the first thing I would ask as a quiz before we even begin solving the problem, like a 5-minute quiz. Just by inspection, find out what the zero force members are. Okay, I started the pin at A. Obviously, the pin at A is going to have many things going on, because I'm going to have FAI, FAB, FAK, then I'm going to have AX, and then AY. So there is nothing special going on there. But I immediately look at the pin at K. Look at the pin at K. Okay, if I draw the free body diagram of the pin at K, right, I'm going to have FKB. Okay, this is not straight. I never for the life of me, sometimes, these things, I tell you, okay, FAK, I don't want to bicker early in the morning. FBK. Okay, so this is going to satisfy the first criterion. Okay, so first criterion satisfied. Okay, so which means that both of these become zero force members, and then because I've already looked at this problem a good number of times, I can tell you that there are no other zero force members. I would like you to inspect it carefully, go step by step, and then figure it out, okay, and then say, okay, there are no zero force members besides this, other than the one at GE or EG, that's a zero force member there, and besides that, by inspection, I cannot find out any other zero force member. Okay, so I could draw the Venn diagram at G. If I did that, right, I'm going to have FGE, and then FGH and FFG. Okay, FGF and then FGH or HG, and then I automatically figure out that, okay, both of them, one of them is a zero force member because the other two are collinear. Here these two are gone, and this is based on the third criterion. Okay, so third, satisfied at the pin at G. Okay, this is the first criterion satisfied at the pin at K. Okay, so these are the only zero force members that I can find out in this problem. The good news is that the problem does not necessarily want me to find the force values of these bars. It's asking me to find the forces on other bars. Okay, so the forces that I need to find out are on FED, FEH, and then FGH. Okay, so how do I do that? Using the method of sections. Okay, so here is the basic idea. So we're done with finding the zero force members. So maybe just make a small note here. So the zero force members are, okay, so these are GE, then AK, and then BK. Okay, so we found this out. Then I move on to the next part of the problem. Before I move on to the next part of the problem, I want to make a small note. Okay, so in the method of sections, okay, it is based on the premise that if the truss is in equilibrium, then every part of it is also in equilibrium. Okay, so since the truss is in equilibrium, every part of the truss is also in equilibrium. Okay, so which means that if I take a bar of a truss, then that bar of a truss is also going to be in equilibrium. Okay, and this is the basic premise for the method of sections. And then typically what I also do is I always start and I insist you do the same. I always start by assuming each bar of the truss to be in tension. Okay, and as you think the method of sections, right, it has the name section. What do you mean by section? Section means I cut through something. Okay, so section means sectioning. Okay, section implies that cut through. Okay, which means that we're going to cut through the bars of interest. Okay, and before I go ahead and talk more about this, the basic idea is if I take a bar of a truss, let's say that I have the bar of a truss I have drawn here. Okay, so let's call this as a bar AB. Okay, and if I assume this bar to be in a state of tension, okay, so let's say that this is FAB, this is FAB, and then this is assumed in tension. Then if I make a cut through this bar, okay, so if I slice, okay, or if I section this bar, so this is how I typically look at a section the bar at some point between A and B, right? It's almost like taking a piece of Kit Kat and then breaking it apart. The break has to be clean. Okay, so what do? If I section the bar at this point, then here is what I end up having, right? I'm going to have this piece here, okay, and then I'm going to have this piece here. Okay, so those are the two pieces that I have. I'm just going to draw them out a little apart, and then what will I see? So this is A, then this is B. I'm still going to see the same force FAB on each of those sides, so I'm just going to copy that and paste that here. I'm going to copy that and then paste that creature here. But then, and then here is the section, right? So here was the section that you had cut through. Let me copy that. Let me copy that and paste that here. So this was the section passing through there. It was the same section passing through there as well, right? But then these bars are not in equilibrium, so that in order to put them in equilibrium, I have to have another force on this side. Okay, so which is going to be the same as FAB. This is also going to be the same force FAB. Okay, and so the basic idea is this. If I take a bar in tension, if I assume all the bars to be in tension, and if I section through the bars, then the force at the cut will always point away from the cut. Okay, so this is the cut, this is the cut or the section. Okay, so if I assume a bar to be in tension, assume the bar to be in tension, then when we section the bar, when we cut or section the bar, then the force at the cut will point away from the cut. Okay, so the key word here are the following. If I take a bar of a truss and then if I section it, okay, so if I assume the bar to be in tension, then the force at the cut will point away from the cut. If I assumed it to be in compression, the force at the cut will be pointing towards the cut. Okay, in this case the force at the cut is pointing away from the cut, as you can see from the figure that I've just drawn above. Okay, so this is a basic idea that I'm going to be using for each and every part of this problem here. Okay, so these are some points that I'm making on the method of sections, and more importantly, when do I use the method of sections? Okay, so when to use method of sections. Okay, basic idea is the following. I can always take a problem in truss and then solve it using the method of joints, but then sometimes I will have to solve for hundreds and hundreds of bars of a truss. If I'm laying out a bridge, or if I'm developing the structural framework for a home, I'm going to have like thousands of bars of trusses, right? I don't have time in my life to start looking at the force in each bar of a truss by doing the method of joints. I'm going to grow pretty old if I do that. It's of no use to anybody as well, and it's pretty boring. So method of sections gives me a much more elegant view, or an elegant method to say, okay, hey, I am not interested in all the bars of a truss. I am interested only in some of the bars of the truss. These bars could have been pre-selected because they are the ones that are carrying probably the largest loads, and they are the ones who are susceptible to failure. So I'm going to say, okay, hey, I'm interested in only these 3 or 4 bars here. Can I find the force in these bars quickly without going through the whole rigmarole of drawing the pin free body diagram at one and every pin, and then drawing sum of the forces in X, sum of forces in Y, and then by the end of the day you just tear your hair in frustration, right? So the method of sections is used when I need to find forces in only a few of the bars, and this offers a much more elegant way of finding those forces out. Okay, so when I need to find the forces in only a few of the bars of the truss. Okay, most problems will use a combination of method of sections and joints. Okay, so most problems though, okay, use both method of sections and joints, and this is something that you will see in my next video, and I'll also maybe make a brief note of it towards the end of this video if we have time. Okay, so this is the idea, and couple more things. I think I want to maybe list them as individual points. Okay, so let me say, okay, this is the first point, then this is my second point, okay, then this is my third point, this is my fourth point, this is my fifth point. Okay, then I come to my last point. Okay, when I section through a truss. Okay, so when using the method of sections, we cut our section through let me write that properly. We cut our section through the bars of interest, making sure that we do not cut through more than 3 unknown bars at a time. Okay, this is an important statement. The important word here is this: 3 unknown bars at a time. Okay, and the reason for this is because when I cut a truss, I analyze the truss using the equations of rigid body equilibrium. Okay, so the reasoning for this, the reason when we cut or section a truss, we analyze the cut sections using rigid body equilibrium equations, using 2D rigid body equilibrium equations. And since we have only 3 equations of equilibrium in 2 dimensions, and since we have only 3 equations of equilibrium in 2D, we cannot cut through more than 3 unknown bars at a time. Should not cut through more than 3 unknown bars at a time. Okay, this is the reason. And you'll see as you solve more problems, and as I solve more problems, you'll see what I mean by what I'm saying here. Okay, now I go back to my problem. Okay, and typically in most problems where I use method of sections, I have to find the support reactions at the support points. Okay, and this is my last thing that I'm going to write, F and then G. For most problems involving method of sections, we need to obtain the support reactions first at the points of support. Okay, so this is the last thing, which means that I have to first draw a free body diagram of the entire truss. Okay, so which means that draw the FBD of the entire truss and then obtain support reactions. Reactions at the supports. And this is precisely what I'm going to be doing next. Okay, so I'm going to go back to our problem. I think I'm going to risk it and see if I can maybe just say, if I paste it out here, will it come out? I'm not sure. Well, that did not work out too well. Okay, so I'm just going to go back and then look at our problem and copy that from the beginning. Okay, so here is our problem. I had a roller support, I have a pin support, and then I have all these applied forces acting on the truss. So I'm going to go and bring that down here. Okay, let's see if I can paste that here. Okay, so here is the situation. Now I'm going to remove this guy here because I know that there are reaction forces there, so I'm just going to draw the reaction forces. Okay, so I'm going to cut that out, and then I'm going to have my reaction forces. There is a roller here, which means that there's going to be only one reaction force, which I'm going to call as F suffix Y. Okay, then there was a pin at the point A, which means that I'm going to have 2 reaction forces, which is AX and then AY. Okay, all right. I need to find the forces. I can then say that, okay, here is my coordinate frame xy, and then counterclockwise rotations are positive, right? This is something that you typically do for each and every problem that you solve in rigid body equilibrium. Okay, all right. So what do? Sum of all the forces in the x direction is equal to 0. Let me start off with that. Okay, forces pointing to the right are positive. What are the forces? Ax and then the 40 and the 30 kilonewtons together. Okay, so let me write that out. So Ax is pointing to the right, minus 40 minus 30 is equal to 0, which tells me that Ax is equal to 70 kilonewtons. Okay, so that's something that we found out. Then can I do sum of forces in the y? It is not very useful. Let me do the sum of the moments about the point A. Okay, let me do sum of moments about the point A and then set that equal to 0. Let me write my summation carefully. So all right, if I do sum of moments about A and then set that equal to 0, what are the moments that I have? Okay, the force Fy times a distance of 4 meters. Okay, 2 meters plus 2 meters, 4 meters is a clockwise moment. So Fy times 4. Okay, then I'm going to have the vertical 40 kilonewton force. This is going to have a clockwise moment 40 times 2 about the point A. Okay, and I would like you to go through this exercise, okay, as you're solving this problem. And then this 40 kilonewton force, distance of 1.5 counterclockwise. And then the last one is the 30 kilonewton force times the distance of 3 meters, all of that equal to 0, which I can solve for Fy, and I get Fy is equal to 57.5 kilonewtons. Okay, so that's the second thing I'm doing here. So that's the first thing, the second thing, and then the third thing is I can sum forces in the y direction and set that equal to 0, and I will end up having Fy plus Ay minus 40 minus 50 is equal to 0, which means that I can solve for Ay, and let me make some space for myself to write out Ay. I'm going to scoot these creatures up here. Okay, fantastic. So that I can write out everything down here. So Ay, well, that did not work out too well for me. I'm going to cut that off and write Ay is equal to 32.5 kilonewtons. Okay, so this way I have found out all the forces that are of interest to me for this particular problem, all the support reactions. Okay, this is one of the key steps that you perform in this particular problem. So whenever you do method of sections, the first thing you do is, okay, hey, can I find the support reactions? And if you can, then that is what you should be doing, and that's exactly what we've done here. Okay, and I'm going to get rid of some of these tick marks. I don't like ticks, neither should you. All right, okay, that was a pretty silly joke. All right, then what do? So I have all the support reactions calculated. So let me grab this figure. I think I already grabbed it, and then I'm going to put it down here. Well, no, that was a tick. All right, I'm going to grab my figure with the XY coordinate frame that I've set up here, and I'm going to bring it down center and straight. Okay, here is what we have, and Fy is known to me. Okay, Fy, we found this out to be 57.5 kilonewtons. Okay, Ax was going to be 70 kilonewtons, and then Ay, we found this out to be 32.5 kilonewtons. Okay, so we found out all of these things. Now what do? I am told to find the forces in the following bars. Okay, so we are told to find forces in the bars ED, EH, and GH. Okay, so which means that, I put a small tick mark next to these bars. I'm just going to bring this down there. So I put a very small tick mark next to these bars. Okay, so here is that bar, and then here is that creature, here is that creature, right? And then what I do is I pass a section through the bars, breaking the truss into two clean pieces. So this is very, very important. Okay, So pass a section through the bars of interest. Bars of interest no more than 3 unknown bars. Unknown bars meaning no more than 3 bars whose forces you don't know. I don't know the forces of the bar ED, EH and GH. So that is okay for me. I am just passing to 3 of them, right? I cannot pass the force. I cannot pass a section through ED, EH, GH, HC and DC and then break it up into some kind of a nonsense piece, right? That is not possible for me, okay? So pass a section through the bars of interest, no more than 3 unknown bars, and then break the entire truss into 2 clean pieces. Always imagine breaking a piece of Kit Kat. If I'm taking the Kit Kat piece and then holding it at one end and my other finger at the other end and I'm snapping it through, I'm breaking it into 2 clean pieces, okay? If you're strong enough, you can do that. Okay, all right. So here is what I'm going to do. Break it into 2 clean pieces. So I'm going to make a cut through each of these. Okay, so here is my cut. Okay, this is the way I'm cutting, or this is my section. I'm just going to label it. This is my section. Okay, and what will happen because of that? Here is what, this is a good section. Okay, so this is a good way of sectioning it. I'll tell you what is not a good way of sectioning it. Let me maybe grab my figure from here. Okay, so let me do good versus not good. Let me have 2 figures on the side. Okay, so this is one and then this is another one. So good versus not good. Let's see, can I bring all of them? Hang on a minute. I need to maybe move this on further to the side. Let's see if I can bring the other one here. All right, so good section versus not a good section. Here is a good section. Okay, this is good. I'm cutting through these 3 bars. This is a good section. Good way of sectioning. A bad way of sectioning is the following. Okay, let me put that in the red color. A bad way of sectioning is, okay, I'm going through there, here, and then I'm cutting through here, and then doing something like that. That is a bad way of sectioning. I'm passing through more than 3 bars. I'm cutting it in some willy-nilly fashion. I'm just taking a pair of clippers and then going crazy. I'm not doing a haircut here. I'm doing a section cut through the truss. Okay, all right. So this is a bad way of sectioning. Okay, so do not do this. Okay, always do it this way. All right, so now I have this way of sectioning done. I'm going to bring it down here. Okay, I'm going to bring my figure from here. This is the one that I actually wanted to work with all the values calculated and so on. I'm going to copy that and I'm going to bring it down here. Okay, and I'm going to remove these tick marks somehow. Let's see, I'm just going to use the eraser to remove these things. Okay, and as I'm doing the sectioning, I'm going to break it into 2 clean pieces, and you're going to see this now. Okay, so let me show you how I'm going to do that. I'm going to copy this and then paste that here. I'm going to get rid of that. I'm going to cut that off. Watch me. Okay, I'm going to cut this off as well. I'm going to keep this on here. I don't need it. And watch this. I'm going to draw 2 pieces of the truss now. Okay, here is the first piece and then here is the second piece. So here was the section through which it was cut, and then here is the first piece of this truss that I'm going to be drawing. I'm going to copy that piece and then paste that down here on the side, and I know that this is the answer to Fy, so I'm just going to leave it there. Okay, Fy is this much, and let me make sure that these are aligned nicely. with the straight lines. All right, fantastic. And this is what I have. And then here is what I'm going to do further. I'm going to take the other piece and I'm going to draw it onto the other side here. I'm going to copy that and I'm going to bring that down here. Okay, I'm just going to show it on the side of this piece here. Okay, so here is the way we sectioned it. I'm going to bring my section guy. Okay, so I'm going to copy that and then first of all move it through here because I know that this is how we sectioned it, and I'm going to draw this out here as well. Okay, so this is a way we sectioned it. This was the way we sectioned it. Okay, and let me make sure everything is aligned well. All right, fantastic. Now we are good to go. Now here is what I'm going to do. Through all the bars that I have cut through, okay, let me take this and bring it. That was unnecessary, I guess. Okay, let me just leave it like that. Through all the bars that I sectioned through, I'm going to put a force through them. Okay, so as I told you, right, if I'm cutting through a bar, and since I'm assuming each of the bars to be in tension, the force along each of the bars are going to be pointing away from the cut. Okay, so these are all going to be pointing away from the cut. Okay, and this is the line through which I'm drawing them out. Okay, and I'm going to do one more thing. I'm going to just complete this triangle here with the dotted lines. Okay, and I'm not drawing that section out. Those are all like ghost lines. Essentially, they are not there for me. I'm just going to ignore their presence. I'm just going to tell you that, okay, let me try drawing it as a dotted line, and then let me bring the force out again there. That's good. And likewise this as well. So I'm going to say that these are all dotted lines. Okay, and likewise I'm going to do the same thing on there as well. I'm going to say, okay, hey, there is going to be a force through here. Okay, there is going to be a force through here as well. Okay, and then there is going to be a force through this bar here through which I cut. Okay, and so I'm going to write down the forces that I'm exposing out on these bars. Okay, so this is going to be the force F E D, then this is going to be the force F G H, and then the last one is going to be the force F E H. Okay, so this is going to be the force F E H. Okay, so these are the things that I have here, and you can essentially also see that I have a slope triangle that is given to me, right? Essentially that this is a height of 1.5. Okay, so that's something that you can write down here. So if this is 1.5 meters, then I have a slope triangle of 1.5, 2 and 2.5, or 3, 4 and 5. Okay, so that's a 3, 4, 5 slope triangle that I essentially have. So I'm just going to draw that slope triangle. So this is going to be 3, this is going to be 4, and this is going to be a 5 slope triangle. Okay, and likewise I'm going to have F E D on this section, I'm going to have F E H on that section, and then F G H on that section as well. And the basic idea is the following. If I look at either piece 1, okay, so this is piece 1, or if I look at piece 2, whether I look at piece 1 or at piece 2, I see that there are no more than 3 unknowns. Okay, there is FED, FEH and FGH. No more than 3 unknowns, right? Which means that I can use equations of rigid body equilibrium. Okay, so next step is this. So I can analyze either piece 1 or piece 2 using rigid body equilibrium. Equations. Okay, and the choice is mine. Do I want to analyze the bigger piece or do I want to analyze the smaller piece? Obviously, it's a no-brainer, right? I'm going to analyze the smaller piece, and then you recognize that if I did not find out the support reactions to begin with, then for each of the pieces I would have had more than 3 unknowns. Okay, that's also something I want to find out and point out. So if we had not found the support reactions to begin with, then each piece 1 and 2 would have had more than 3 unknowns. Okay, this is something that you really want to be very sure about. Okay, and so because of that, I can because of the fact that we spent some time finding the support reactions to begin with, now I can analyze the problem directly. Okay, and that's exactly what I'm going to be doing. So I have the support reactions at Fy and Ay and Ax. Ax was 32.5 kilonewtons. I'm sorry, 32.5 kilonewtons. And so I can either analyze piece 1 or piece 2, and my choice is I'm going to go with piece 1 because it is the smaller of the two pieces. Okay, so I'm just going to copy this piece, and so I'm going to analyze. So let me choose to analyze piece 1. Okay, and you can do either piece 1 or piece 2, it is your choice. Okay, all right. So here is what I have. So this is piece 1. What are the things I could do? My thought is, okay, what is the fastest way to solve this problem? Here is what I can do. I can sum moments about the point E. Look at this. If I sum moments about the point E, so let me write this out here. Let me get rid of this and then say, okay, this is piece 1 here. So let me sum moments about point E. I can sum moments about multiple points. Okay, that's my prerogative. I can sum forces in the y direction, forces in the x direction, and so on. I can do pretty much whatever I want, right? So for some moments about the point E, look at this. The line of action of EH is passing through E. Line of action of ED is passing through E, which means that only the force FGH is going to cause a rotation about that point, and then Fy is going to cause a rotation about that point. The 40 kilonewton force is also sitting at the point E. Okay, so I'm going to have FGH times the distance of 1.5. And this is going to be in the counterclockwise direction, and then I'm going to have Fy times the distance of 2 meters clockwise. If I did not find out Fy, then I could not find out Fgh, right? I could not have found out Fgh, so I have to find Fy to begin with, which is why we spent time doing the support reactions. And I can solve for Fgh. Okay, once I do this, I get this to be approximately 77 kilonewtons. I get this to be positive, which means that Fgh is in tension. Okay, so that's the first thing. So I found out Fgh. Then I can do, what else could I do? I could sum forces in the y direction. Okay, so that's exactly what I'm going to do. Feh, if I take Feh and then break it up into its components, right? So this is Feh. I can break it up into a component this way, and then I could break it up into a component this way. Okay, so the slope triangle is 3, 4, and 5. Okay, so this is going to be 4/5 Feh, and then this is going to be 3/5 Feh. Okay, if I sum forces in the y direction, here is what I can do. Sum of forces in the y direction, all the forces pointing up are positive. Fy is pointing up. Then I have the 40 kilonewton force pointing down and 3/5 Feh pointing down. Minus 40, 3/5 Feh, all of them put together is equal to 0. Okay, so which means I can solve for Feh, and I end up getting this to be around 29.2 kilonewtons. I get this to be positive. Feh is positive 29.2 kilonewtons, which means that Feh is in tension. Okay, so I have found out 2 of them. Feh has been found out, and then you obviously know what to do next. I just sum forces in the x direction, and I can find Fed. Okay, or I could also do the other thing. This point is the point H here, right? I could also sum moments about the point H. Let me do it both ways. Okay, let me sum forces in the x direction and set that equal to 0. Okay, if I look at the forces, I'm going to have Fgh, Fed, and then 4/5 Feh, all of them pointing to the right. Okay, so FGH, FED, 4/5 F, EH is equal to 0, so that FED is minus FGH minus 4/5 FEH, so that FED will end up being a negative value, okay, approximately minus 100 kilonewtons, which implies that FED is equal to 100 kilonewtons in compression. Another way to find FED is the following. Okay, I'm just going to take my figure from here, grab this one, and then bring it down here. I can sum moments about the point H. Okay, I can use the sum of moments multiple times if it makes sense to me to find out what I need to do. Okay, I could sum moments about the point H and then set that equal to 0, which automatically tells me, okay, hey, FGH is gone, FEH is gone, because both of them have a line of action passing through the point H. FED times the distance of 1.5 negative clockwise moment, and then FY produces, excuse me, this distance here from G to H is a distance of 2 meters as well. Okay, so Fy times the distance of minus 4, Fy times 4, because that's also clockwise. Okay, and then lastly I have the other force. Don't forget this 40 kilonewton force, 40 times the distance of 2 meters in the clockwise direction and counterclockwise direction. So 40 times 2, all of them equal to 0, and if I solve for FED, I end up getting the same answer as before. This is approximately minus 100 kilonewtons, or FED is 100 kilonewtons in compression. All right, so that's essentially the end of this problem, where we use the method of sections, and the basic idea is very easy to understand, but it's hard to implement because we have to go through rigid body equilibrium. Okay, but here is the basic idea. So I start off with the problem in hand, and I'm told to find forces in all these bars. Okay, my first step is typically find out all the support reactions, Fy, Ay, and then Ax, to begin the problem with. Then I section through the bars of interest. I section through no more than 3 bars of interest, and as I do that, I break the truss into 2 clean pieces. Okay, that's essentially what we've done. This is a bad way of sectioning. This is the good way of sectioning. Don't section through more than 3. As you section, you break the truss into 2 clean pieces, as you can see here. And then, since I assume all the bars to be in tension, all the forces on these bars are pointing away from the cut. They're pointing away from the cut. They're pointing away from the cut, and likewise here as well. Okay, and then the next thought is, okay, do I analyze either section 1 or section 2? I can do either one of them, piece 1 or piece 2. I take the smaller of the two because it's looking easier for me, and then I go through the equations of rigid body equilibrium for that particular piece. Sum of moments, sum of forces. Sometimes I can use sum of moments multiple times to find out the answers to the bars that I'm interested in. Okay, in this problem I use sum of moments at E and at H to find out FED and FGH, and then I can use the sum of forces to find FEH. Okay, and so this was the basic idea. And the moral of the story is, you need to know both the methods very well, method of joints and method of sections, because most problems you're going to use a combination of both the methods. Just one method is not going to be enough for you to solve the entire problem. All right, I hope the video made sense. We will solve a few more problems next week on method of sections. I hope all of you are staying safe. Take care of yourselves. Bye-bye.